Hi everyone, today I'll be presenting my project on Danish house price prediction as part of the AI and deep learning course. So today I'll be walking you through the problem specification, how I sourced the data, what models did I train, and some preliminary results I got at this stage. Housing is a hot topic all over the world. This is especially so for Australia, where we currently see housing crisis and economic uncertainty. So the need for accurate and data-driven insights is huge for all parties, buyers, sellers, investors, and policymakers. To address this, I formulated a supervised regression problem aiming to predict house prices using some property characteristics as well as macroeconomic variables. While I was initially interested in Australian housing market, I chose to work with the dataset which was publicly available on Kaggle. It's a Danish housing transactions between 1992 to 2024. It contains 100,000 observations, and yes, it's publicly available and can be accessed by everyone. Before modeling, I did some data cleaning. I dropped some missing variables, missing observations. Then I dropped some observations where year build was later than year of transaction because the difference for up to 30 years seemed to be a bit suspicious. So those observations were dropped, and I did some variable renaming so it's easy to work with them. I applied one-hot encoding for categorical variables and normalization for numeric variables, and also transformed transaction date so it's better suited for the modeling purposes. As a result, I ended up having the independent variables you can see in the table. As my target variable, I chose to work with average prices per square meter in Danish crowns rather than total prices for two reasons. First of all, there is less variance due to property size when I predict prices, and also the distribution of average prices is less skewed than the total prices. So at the last stage of pre-processing, I split the data into training, validation, and test in the proportions you can see on the screen. So, key findings from EDA. On the left-hand side, you can see the distribution of average prices on the top and total prices on the bottom. And this is the skewness I was talking about on the previous slide. On the right-hand side, you can see the different types of houses and how common are they in the dataset. Also, the age of the houses in each of the house types. So we can see that most of the houses are 20 years and older, and villa being the most common type of house, while farm is the least popular one. I also looked at the price changes across the years. Here we can see that the prices followed an upward trend, but in general, they are distinct for different types of buildings. And I also incorporated some macroeconomic variables such as interest rate and inflation to better capture that variance in the prices that we see. This box plots shows the distribution of average prices across different regions and sales types. And here we can also see some outliers, but they were kept as a part of the analysis as high-end properties is a natural part of real estate market. So all in all, we can see that transaction and property characteristics have some predictive power and can be used in predicting house prices. Let's look at the model architecture now. At the baseline model, I used random forest, which outperformed the other two initial models. So I used these three metrics you can see in the table: mean squared error, RMSE, and R-squared. So random forest explains almost 60% of the variation in prices, and the hyperparameters were tuned via randomized search with cross-validation. This graph compares actual values to predicted values using random forest. So here we can see while random forest is performing well for low to mid-priced houses, it tends to underestimate high-end property values. Next, I trained wide and deep model. So this model consists of two parts, wide part and deep part. So the wide part, on the right-hand side, you can see there is this structure to make it easy to understand. So wide part consists of only one layer with one neuron and linear activation function, while the deep component has three dense layers with ReLU activation function and some dropout for regularization. And the final output is the sum of these two components. And on the next slide, we can see how this model performs. On the right-hand side, you can see training and validation loss decreasing over the epochs. And here, validation is below training loss, which is likely due to the dropout, which was implemented to prevent overfitting. However, performance on overall was weak compared to the benchmark random forest. So here we can see that wide and deep model explains only 38% of the variation in the prices, and its RMSE is higher by 2,000 Danish crowns. Inspired by the combined actuarial neural networks covered in this course, I decided to train a hybrid CNN where I combine random forest with neural networks. So while the traditional CNN includes GLM plus neural network, here I decided to replace it with random forest because random forest performed better in benchmarking. So on the right-hand side, you can see the structure where random forest and neural network are trained separately, and the output is averaged using some weighting. On the neural network part, it's pretty similar to the wide and deep model I trained before, the deep part. And the random forest parameters were chosen similar to the ones used in benchmarking. So the results show that this model performs better than the wide and deep model I trained before, but it's still lower than the benchmark random forest. It explains only 54% of the variation in the prices, and its RMSE is higher by 600 Danish crowns. Clearly, random forest performs best on this dataset, especially for mid-range prices, while for the neural networks, there is still room for improvement. And the next focus of this project would be to do hyperparameter tuning to see if the predicting accuracy can be improved. That's all on my end today, and thank you for your attention.